don't mind me asking questions, no?
No, yeah, ask.
Is it okay?
That's why it's in person, so you can like interact more.
Interrupt often?
No, it's okay. I hope they can like on the stream, your voice will be recorded. So if somebody else ends up, watching later, they can hear the questions.
No, that's completely fine. It's just, yeah, I'm a bit worried about interrupting my class, but if you're fine with it.
I don't know. Questions are important. Okay, let me find it. Setting things up. Okay. Questions are important. Okay, let me find it. Setting things up. Okay. Questions are important. Okay, let me find it. Okay, I'm gonna mute this.
Week of classes.
It was fine. It was fine. Oh yeah, people are joining. Okay. Hello, Albie.
Hello.
Okay, so we'll wait a couple more minutes. If nobody joins, we're gonna start. Oh, that was practice. So it was like rehearsing for explanations. Oh yeah. Okay. I hope I don't forget this. Okay, so nobody showed up. I'm gonna start. Okay, hello everyone. Look at this amazing audience. We only got one person. Nobody showed up. Inner products. Okay, so in high school, you should have heard. Can they see me? They can see me. Okay, so in high school, you should have heard of inner product. Oh, not inner products. You should have heard of the dot product of vectors. So what was the dot product? So if you had a vector x with these coordinates and y with these coordinates, then the dot product of x and y was defined to be the sum of the pairwise product of their coordinates, right? So x1, y1 plus all the way this to x and y1. And this product has several properties. And the important ones were that it was, you could say, commutative, that it was, homogeneous. Right, so if you multiplied one of them by a constant, this is the scalar multiplication, then it was the same thing as if you just multiplied the whole product. And what were the other ones? Wait, and then based on this, we defined the notion of the length of a vector, where we said that the length of a vector x is equal to the square root of its dot product with itself. And this came from the Pythagorean theorem, because, well, if you multiply x by itself using the dot product, you get x1 squared plus x2 squared all the way to xn squared, and then if you root this, you get the Pythagorean theorem, so that would be the length of a vector x. some of the implicit properties of okay, question.
Would you mind showing a visual example? I just can't.
A visual example. Okay, that's an exercise in the book.
Okay.
Because most of the time we don't have like a precise visual in abstract vector spaces. So I just want to familiarize you guys with the properties.
Okay, and
Yeah.
second question. When we multiply x by y using the dot product, you said that we multiply their respective coordinates together and then take the sum of those coordinates? Or,
Yeah.
and then it all ends up being one value instead of just
Yeah. So
like a matrix or.
yeah, it's gonna be one value, right? So if you have x and y in Rn, then x dotted with y would be in R. It's gonna be a scalar.
Okay.
Right, so if you want to look at this, the operations here, right? This is the scalar product, but this is just regular multiplication in R, right? Because that's a number, so you get regular multiplication, but here that's a number, that's a vector, so you get scalar multiplication. And then the norm. Okay, so the length, you can't have like negative length, right? And the only vector with zero length is the zero vector, right? So the only vector whose norm is 0 is 0 if and only fx equals 0. So what this means is that if x isn't 0, then this is the contrapositive. Then the inner product of x, not the inner product, the norm of x, the length of x, isn't 0. So if you square this and you see what it's equal to, it's going to be x dot x from the definition. That means that this isn't 0. And furthermore, because the length can't be negative, we don't have negative length, we say that this is bigger than 0 for x not equal to 0. And if x is 0, then that's clearly 0. So these are the properties. I'm going to write this here as well. Okay, so that's for real, so Rn, right? This is for Rn. Question?
Yes, why would we need the dot product and why would we need to know this?
Because we can, okay, so far, that's actually a really good question. So far, we don't have the notion of length, right? So we have all these visuals, but we don't have length, and we don't have angles, right? So once we sort of develop the notion of the inner product, we can sort of generalize length and angles to arbitrary vector spaces.
So functions vectors
Yeah.
also have an angle?
Yeah, and we'll get to that actually,
Wow.
right?
Okay.
But it's in the exercises. So if you look at, well, not angle specifically, but one of the exercises is, we're gonna get to it.
Okay.
Getting ahead of ourselves, okay. So this is for real spaces. What about complex spaces? So again, the whole point of the dot product, like you said, was because we want length. We want length. And in, say, Cn, the n-dimensional vector space over C, how would we define length? So if you have a vector in this, it's going to be, z1 all the way to zn. In Cn, I'm going to call this z. So what would be like a good candidate for the length of z? So in R, we have the Pythagorean theorem, right? Where we take the absolute value of each of these vectors and we square them, add them up, take the square root. That's the length. So we can get the same, just sort of pick up the formula, put it here, and what we get is we get c1 squared all the way to cn squared. And okay, now I want to talk about conjugates. So I don't know in A22 how much we did about conjugates, but if you have a complex number, say x, right, and x is equal to a plus b I, the conjugate of x is equal to a minus bi. So if you want a visual for this, this is the complex plane. real axis, imaginary axis, and we have x. And this would be, of course, a, this would be bi. The conjugate of x is the reflection of x with respect to the real axis. So that would be negative bi. Okay. So a nice property of the conjugate is on the length of a, so in the complex plane, we have a, bi. The length of this vector, x, what was I going to say? Oh yeah, we can use the Pythagorean theorem to find the length of x, right? That would be, because that's a, it's b, we have length of x squared is equal to a squared plus b squared. So the length of x is equal to a squared plus b squared square root.
How come it's b squared, not bi squared, which would make a squared minus b squared?
The thing is the length of I, so I visually is this, right?
Yes.
bi has a length, right? And usually with lengths, and well, I should have, we're gonna get to it later, but with lengths, if you have bi, or bx in general, it's gonna be equal to the absolute value of b times the length of x, right? It's like if you have x, and x is of a certain length, and you scale it b by b, the length of the scaled vector is gonna be bx. Well, b times the length of x.
Okay.
Right? And if you have I here, the length of I is 1.
But then don't we need a negative in front of b?
Well, why would we need a negative?
No, because you said that we.
Well, length can't be negative. You're finding the length of. See?
Yeah.
Oh, yeah. Yeah, so the length of bi is just b, the absolute value of b. So yeah, now, so in summary, we have the magnitude of x, in the complex numbers we call this the magnitude, is equal to the square root of a squared plus b squared. One nice thing about the conjugate is you can sort of, you know, when you see this, you think of difference of squares, right? So if you multiply x by its conjugate, are they asking questions? They're not asking questions, okay. So if you multiply by the conjugate, you get a plus b I times a minus bi. By difference of squares, that's equal to a squared minus bi squared. Now, bi squared is b squared times I squared. I squared is negative 1. That comes out and turns this into a positive. So what do we get? We get that the product of x with its conjugate is going to be the square of its length. That makes sense? I hope that makes sense. Question?
And yes, why for the formula for the length of x, there at the top under the radical, why did you put absolute value around 0? Does that denote?
Around what?
No, you surrounded z in absolute value brackets, didn't you?
I should have introduced notation, right? So this is different from this. Right, these are two different operations. This in R and Z, this is defined in R to be the absolute value. And in C, it's defined like this, where x is equal to a plus bi, right?
Okay.
But in vector spaces, you have the norm, right? And the norm is the same thing but twice, two brackets.
Mm-hmm.
And that's equal to the square root of x dot x.
Okay, thank you.
And what we get is that the product of x with this conjugate is going to be the square root of the length of x. Now when we look at this sort of definition that we made up for norm, we have all these absolute value squareds, right? So we can write them using what we have here. This is the dirty one. We can rewrite this using that. So it would become, well, this is just equal to the product of z1 times its conjugate we can go on until the end. And the whole reason we're doing the inner product in the first place is because we want the norm, or the length of vectors, to be equal to the square root of the dot product. So, and notice this sort of looks like the definition that we had for the real dot product, because we're multiplying two things and then adding them up. So what we can say is that this is equal to wait, how would I say this? Z1 dotted, not dotted. Okay, so you want this to be equal to the square root, and z is this vector, of z dotted with itself. That means that this inside thing has to be equal to this. And notice that the second one is always conjugated, and we have z here. So one thing we can say is, if you want to define an inner product such that this works, we can define the inner product of z with w, where w is in Cn, to be z1 w1 conjugated plus z2 w2 conjugated all the way to zn wn conjugated. So this would be a definition for dot products in Cn. Now, notice that if any of these are real numbers, right? If you have a real number, that's equal to a plus 0i in general. And if you take the conjugate of this, that's equal to a minus 0i, which is just a, right? So if you conjugate a real number, you get itself back. So for instance, if w1 and w2 and all these, if they're real numbers, then this dot product reduces to the special case of the real dot product, because these are just equal to themselves. So that basically tells us that to study inner products, which are the generalization of the dot product, we can look at the complex properties, and whenever we want to talk about the real numbers, they just come up as a special case. Yeah, and then so to update what we have here, we only need to update these two, because now notice, it's no longer commutative. This operation is no longer commutative because the second one is being conjugated, right? But one nice thing about conjugates, and I'm not going to prove this, it was probably proved in 822, I'm not sure. If you have two complex numbers, a and b, right, then the conjugate of a plus b is equal to the conjugate of a plus the conjugate of b. I hope they can see. And then the conjugate of a times b is equal to the conjugate of a times the conjugate of b. We can use that to notice something, right? If you conjugate all of this, what we get is, so we're going to conjugate each of these, but once we conjugate these, oh, and I forgot. A conjugated twice is equal to a. Because remember, geometrically, it was reflection about the real axis. If you reflect it twice, it goes back to where it was. And where were we? Right, so if you do this operation using those rules, what we get is this is equal to z1 conjugated times w1 times z2 conjugated times w2, all the way to zn conjugated wn. Now this, by the same definition that we used, would be equal to w dotted with z. So instead of the commutative property, we got this property, that the conjugate of z dot w is the same as w dot z. So we can update this and say that we have that, and this is going to be called conjugate symmetry. And these are the properties of inner products. We're going to generalize this. We're going to say any operation on any vector space, right? So suppose we have a vector space V, over the field F. And the reason it's called inner product is because we're going to put it inside something. We're going to put it inside brackets. We're going to have this operation where dots just indicate something to place there. From V times V, the Cartesian product of V with itself, to the field F. And this operation, if it wants to be an inner product, wants to have these properties. That x dotted with itself is greater than or equal to 0. That, oh, I forgot distributivity. I knew I forgot something. Oh yeah, and the other thing with the dot products was that they were distributive. Right, so if you dotted x plus y with z, it would be x dot z plus y dot z. Yeah, so the second one is homogeneity. So lambda x dotted with, not dotted with, the inner product of lambda x and y is equal to lambda times the inner product of x and y. And lastly, yeah, the distributive property, which the textbook calls additivity, that x plus y, its inner product with z, is equal to x inner product with z plus y inner product with z. Now notice, this only works in the first slot because of conjugate symmetry, which is the last one. That xy is equal to yx conjugated. Why does this only work in the first slot? Because, well, I'm going to erase this. Yeah, because if you have, well, actually it does work in the second slot. Well, let's try it, right? So we have z, x plus y, by conjugate symmetry, this is equal to x plus y, z conjugated. That's equal to, conjugate the whole thing, xz plus yz, which is equal to xz conjugated plus yz conjugated. Alright, I'm terrible at drawing the inner products. Okay. And again, by conjugate symmetry, we can flip these, right? We get zx and zy. So it is actually additive over the second one as well. That doesn't work as well for homogeneity because, say if you have x plus lambda, no, the inner product of x with lambda y. By conjugate symmetry, this is equal to lambda yx conjugated. That's equal to the whole thing lambda yx conjugated. That's equal to lambda conjugated times, by conjugate symmetry, the inner product of x and y. So we can see that, yeah, x lambda, the inner product of x and lambda y is not equal to lambda times the inner product of x and y. Right, we have this conjugate on top. So linearity only works in the first slot, not the second slot. You have to remember that. Okay. I think that was it for definition of the inner product. What else do we have to say? There's some other stuff with zero. I'm not gonna talk too much about those. Yeah, the norm. Okay, so the norm, which is the generalized notion of length of a vector v, is, as we said, the square root of the inner product of v with itself. That's the length of v. And this has some properties. I mean, we define these axioms in such a way that we have these properties that the length of V is 0 if and only if V is 0. And that because of homogeneity, what we have is if you have, say, lambda V, and you want to find its length, that's equal to the square root of lambda V. By homogeneity, you pull this out. And you pull the second one out, but remember, it has to be conjugated. So you have lambda times the conjugate of lambda times VV, that whole thing. And if you remember from before, this, so lambda times the conjugate of lambda is equal to absolute value of lambda squared, or the magnitude of lambda squared. So that becomes the square root of lambda squared dV. Since that's squared, we can pull that outside, and we get, and that's just the norm. So this whole thing is lambda times the norm of V. So these are the basic properties of the inner products. Okay, this is where it gets a little bit interesting. So to work with angles, the first thing we have to define is right angles. And like in Euclid, one of his postulates is that all right angles are equal. That's the only thing he says about angles is all right angles are equal. And he defines everything else based on this. So we're going to do the same thing. We're going to talk about right angles first, and then we're going to go on to talk about other angles in the exercises, not in the actual book. Okay, so if you remember from high school, I think this was the formula where we said that the dot product of x and y was equal to the length of x times the length of y times cosine of theta, where theta was the angle between them. Now in Euclidean space, this is all well defined, thanks to Euclid. We know what theta is. And we said that if theta is 90 degrees, that is if they are perpendicular to each other, right? Then cosine of theta is going to be 0, and this whole thing is going to be 0. And we're going to use this notation. We're going to say that in the real numbers, what we said was that x and y are perpendicular to each other if and only if their dot product is 0. So we're going to take the same idea, and we're going to sort of use this to define the notion of perpendicularity for arbitrary vector spaces. So we're going to call this orthogonality, because we need a fancy name. So two vectors, x and y, in V, are orthogonal if and only if their inner product is 0. And if they're orthogonal, we're going to write that as x perpendicular to y. And some notions about this. So 0 times any vector is 0, right? So 0 is perpendicular to everything. And because, remember in one of the axioms, this one, we said that x times x is greater than 0 if x is not 0, right? So that means that 0 is the only vector that's perpendicular to itself. Yeah. Okay, and then we get to the famous Pythagorean theorem. We're going to prove this. I don't think this was proved in elementary school, so the first time we're going to see this. Okay, so what is the Pythagorean theorem? So in Rn, I'm not going to draw that actually. So if you have two vectors that are perpendicular to each other, they end their sum, so we call these so u, v, and then u plus v. They form, if u and v are perpendicular, they form a right triangle, right? So then, from basic geometry, at least in Rn, we know that u plus v squared is equal to u squared plus v squared. The hypotenuse squared is equal to this and that. But we can show this to be true in arbitrary vector spaces or arbitrary inner product spaces, as well as the real Euclidean space. So what are we going to do? Well, u plus v squared, as we defined, is just the inner product of u plus v with itself. And then by homogeneity, no, by additivity, this is equal to u plus v, u plus v, and then again u plus uv plus vu plus vv. Now, because we said that u and v are orthogonal, that means that their inner product with themselves is 0, so those two get cancelled out. So all we're left with is uu plus vv, and that's, from the definition of the norm, just the norm of u squared plus the norm of v squared. And this is just the norm of u plus v squared. So that's the Pythagorean theorem. We're going to use this a lot. Okay, I'll be left. Okay.
So it is just me and you now?
No, the Evan is there. I think he's watching on the stream. I don't know if he's commented. He has. Oh man, I missed the comments. Okay. Expand the screen. Why is it that small?
Scared.
Wait, I never noticed. Why is it? Why is this so small? There you go. Why does it have a... Why is... Okay, whatever. There's a... Didn't change? Oh, it's... Oh, yeah. The quality is so bad, I'm sorry. I'm gonna bring it closer. And then... Okay. Let's continue. Where were we? Oh yeah. I'm gonna bring down something new. So a lot of the time, something we like to do, I'm gonna recall back to high school physics. So, did you guys take physics? No? Okay, great. My example is ruined. Wait. Okay, I'm gonna hope Evan took physics.
You can try to explain.
No, it's fine. Like, it's not complicated.
Yeah,
So
I
if you have a
did.
ramp, and you have an object on this ramp, usually the way, and you want to figure out, okay, so how much should the resistance be on the ramp, right? The friction, so that it doesn't, slip down.
Okay.
Yeah. The way you would do this is you would take into account the force of gravity. But what you actually want is the force, the effect of the force of gravity along the I forgot the word. What? The ramp, that was the word. Along the ramp. And you also want the normal force. And the other thing you want is you want them to be perpendicular so that the math is easy. So what usually you would do is you would drop this, and then you would drop this. I hope Evan can see. in such a way that this is perpendicular. And then this would be your normal force, and this would be the force, and this is parallel to the ramp, right? So if you bring it up here, it's something like that. And you can figure out exactly how much friction you would need to keep it from sliding. And all of this sort of stands on finding two vectors that are perpendicular to each other. Let me write that down. Finding two vectors, v and u and w, so that u and w are perpendicular and u plus w is equal to v. This is called an orthogonal decomposition.
So once we found these two vectors, we basically have the solution to the problem?
Yeah, if you have these two vectors, the solution is easy, right? Because once you have this vector, you know exactly how much force is here, so you know how to calculate the force needed to counteract it.
Okay.
So that's sort of the motivation. But we're going to do this in a general setting, right? So the way I'm going to write it down, it's going to look like as if it's geometry, but we're using the figures to reason about abstract spaces. Where was I? Right, okay, so you have this vector v, and you have this vector u. And you want to find two vectors using u that are perpendicular to each other and that add up to v. So something you could do is you could sort of look at this line, the line along u, and you see that, okay, if you sort of scale u a little bit by a certain amount, you get lambda u, and you connect these two, and this arrow would be v minus lambda u. If you adjust lambda, then you would find something that, such that, you know, lambda u is perpendicular to v minus lambda u. I mean, if you sort of imagine yourself sliding this point, and you can see at some point, this v minus lambda u arrow has to be perpendicular to u. Yeah, so you have to find this lambda that satisfies this equation. And if it does, then obviously lambda u plus v minus lambda u equals to v. So this is the only requirement you have to satisfy. And what does that requirement mean? It means that, and I'm going to drop the lambda here to make our calculations easier. Because notice, if it's perpendicular to lambda u, it's perpendicular to u as well. So what this means in terms of the inner product is that the inner product of v minus lambda u and u has to be 0. So we have to solve this equation for lambda and see what we get. Well, by additivity and homogeneity, we get the inner product of v and u minus lambda times the inner product of u and u. And we want this to be 0. So we solve the equation for lambda, we get that lambda is equal to the inner product of v and u divided by the inner product of u with itself. This, as you know, is the square of the norm of u. So we have the inner product of v and u, and then the norm of u squared. So then we have our decomposition, right? So we know that v is equal to so this is our decomposition, right? So lambda u, lambda is this, so we have vu over u squared, lambda u, so u, plus v minus lambda u, which is just the same thing. So using this method, you know, in Euclidean space, you can find this vector and then solve the problem however you want. This has, and we're going to get to the applications of this that makes it really cool, is that if you have a point in space and you have a line, what is the shortest distance between this point and this line? You guys have any guesses?
Would be
Yeah. So, if you generalize this to higher dimensions and to other spaces, you could potentially use this for approximations, right? And there are examples both in the book and in the exercises, so like Fourier series are in the problem set. And I'm gonna do linear regression as well in lecture. I'm getting ahead of myself. I should not have erased that. That was a mistake. Because I was gonna use it. I'm gonna pretend that's perpendicular. And we have we can use this to, what can we do with this? Yeah, okay, so you know that these two vectors are perpendicular to each other, right? So we can call this, I don't know, like x and y. And we know that these two are perpendicular to each other. You can see from the picture. So, therefore, by the Pythagorean theorem, get that the length of v is going to be equal to this squared, well, that squared. This squared plus that squared, which is going to be the norm of this squared plus the norm of this squared. I'm just going to leave that be, right? We're not going to do anything about that. But this one, I'm going to try to square it. So vu squared over the norm of u squared times the norm of u squared. That's going to be 4.
By norm, you mean
Length.
Okay, yeah.
The thing is, we're in general spaces, so we use the general terms like orthogonal and norm instead of length and perpendicular. Okay, and then that we're just gonna leave it like that. So notice, if we ignore this term, this side is going to become smaller, while this side stays the same size. Therefore, this equality has to change into an inequality. And if we simplify this, right, so if we cancel those two out, and we rewrite this, we're going to get u squared, the norm of v squared, is less than or equal to the magnitude of vu, their inner product. And this is called the Cauchy-Schwarz inequality. We did not have u cubed. We had this was to the 4th power.
Oh, to the...
Because you see this?
Yes.
So apply the Pythagorean theorem to this, right? So if you get the norm of that, right? This is a scalar, so you pull that out and square it, and you get the norm of this and you square it. So at the bottom, this gets squared, so that becomes 4. But the norm of this gets squared and multiplied, so it simplifies. Oh yeah. And then we can use this to prove a generalized version of the triangle inequality. So, yeah, I mean, so this works for, the Pythagorean theorem states that if you have a right triangle, then the square of this and the square of that are equal to the square of this. But, generally, they're not going to be equal. And we can express that using the triangle inequality. So in Euclidean space, if you have, u, v, and u plus v, you can show that using just geometry techniques. that this is greater than or equal to the length of u plus v. That the hypotenuse of a triangle is always shorter than the sum of the two sides. And we had a version of this in, of course, A31, where we had that x plus y, the absolute value is less than or equal to x plus the absolute value of y. So, but to do this in arbitrary spaces, and importantly over complex spaces, the proof is a bit convoluted, and we're gonna skip it. Yeah, you can just read it in the book. Let me check for comments. No comments. Okay. And then there's the parallelogram equality, which the parallelogram law. This also we're gonna skip because it's boring. It says that what does it say? We're gonna skip it. I don't even know what it says. Okay. It has a picture though, so you can look at the picture. Okay. And we're gonna get to orthonormal lists. Yeah. Okay. So I'm gonna get water because the section just ended. I'm gonna get water because my throat. And then yeah, there's a 5-minute break. Yeah. Yeah. Who's watching the stream, by the way? Besides Evan. So Evan is watching, okay. Wow, Robert dipped this one. Didn't even watch the stream. Oh, yeah. Okay. So we get No. Okay. Okay, is everyone here? Ready to start? You guys there? Put something in the chat. Yep, okay. Let's go. Okay, orthonormal bases. Okay, so have you guys watched like the 3 blue 1 brown videos?
I watched some of them.
Some of them?
Not
Okay.
till the spaces.
So you know what I hat and J hat are?
Kind of. Yeah, but
Yeah.
they're only used in R2, right?
Yeah. But the thing with I hat, so I hat was, what was it? It was 1 0, and then J hat was 0 1, right? So if you had that I hat dotted with J hat would be 1 times 0 0, and then it would be 0. So I hat and J hat are perpendicular. They were a basis and they were perpendicular. Such a thing is called and the other thing is their lengths are 1. If you have a basis like this for an arbitrary inner product space, we call that an orthonormal basis. And you have the word is in 2 parts. Orthonormal basis. The word is in 2 parts, ortho and normal. So ortho just means orthogonal. That means the bases are pairwise orthogonal to perpendicular to each other. Normal means that the length of each of the basis vectors is 1. So specifically, right, so you have a basis, and we usually denote an orthonormal basis by E, right? So if you have E1 all the way to En, and let's not say it's a basis, like let's just say it's a list. It's a list of vectors. They must be pairwise orthogonal. So EI must be perpendicular to, I guess, orthogonal to EJ for any I and J that aren't equal to each other. And this would be an orthogonal list. An orthonormal list has the extra condition that EI is equal to 1, that the norm of EI is equal to 1 for all I. If you want to put this more succinctly, because notice this is just, if you square both sides, that's just 1. And this is equal to inner product of EI with itself. What we can say is that a list E1 to En is orthonormal if the inner product of EK with EJ is, I'm going to use this symbol again, the Kronecker delta, if you remember this, at Kj, and this is just equal to 0 if K not equal to J, and 1 if K is equal to J. So this shows up a lot in linear algebra and elsewhere. So I'm just gonna familiarize you guys. Okay, so that's the definition of an orthonormal basis, or list. Sorry. That's the definition of an orthonormal list. If the list happens to be a basis, then we call it an orthonormal basis.
Could you explain what's up with the delta and how is it used and
The what?
what does it mean? The delta.
Delta?
Kronecker.
Kronecker delta. So Kronecker was a mathematician and he did stuff in linear algebra. And why does it show up? So you remember the identity matrix?
Maybe? Yeah.
And then the rest were 0. So this, we called it I, right? what is the index, what is the number at ij? So the ith row and the jth column, depending on ij.
It's either 0 or 1.
It's either 0 or 1, yeah, but where is it 1?
It's 1 along the diagonal, but
Yeah, so what are the coordinates of the numbers on the diagonal?
they're equal.
They're equal, yeah. So if you want to write this, if I and j are equal, if I is equal to j, then this number is equal to 1. Otherwise, it's 0.
Oh,
You see the connection?
yes.
And this shows up a lot. Like if you remember duals had some, and these are actually related to duals. We're gonna get to that. So the dual basis, I'm not gonna go into too much detail, but the dual basis was a list phi k such that phi k vj was equal to delta kj. I'm not gonna talk about that too much, but it shows up a lot. Okay. Yeah. Continuing on. Okay, why are orthonormal bases nice? Well, because we can do the Pythagorean theorem with anything written as a linear combination of these, right? So if you have a list V, not a list, if you have a vector V, and you have an orthonormal list En, if you write V as a linear combination of these vectors, what would be the length of V? And for convenience, I'm going to square it. Well, what we can do is we can group these ones and then have that one alone. These are orthogonal. Why are they orthogonal? So if you have V1, E1, and if you have V2, E2, Vn, En, and you take the inner product, what you're going to end up with is you're going to get, when you expand it out, of course, you're going to get the inner product of E1 and E2, E1 and E3, all the way to E1 and En. Because of orthogonality, those are all 0, right? So all those terms have a sort of a 0 term in them, so this whole thing is going to be 0. And that means that they're orthogonal. Therefore, we can use the Pythagorean theorem on this and say that the length of V squared is going to be the length of this vector squared plus whatever the length of that is, right? So V2, E2, Vn, En squared. As we said, this is equal to the magnitude of V1 squared times the length of E1, or the norm of E1. And for this one, if you just continue applying this procedure, we get the same thing, right? So we get V2, E2 squared, V0 squared, all the way to Vn, En squared. Now this list we said was orthonormal. Because it is orthonormal, all these lengths, all these norms are equal to 1. So the whole thing just becomes this. So it makes finding the length or the norm of a vector pretty easy. And this is one reason why orthonormal lists are nice. Well, the other thing is that every orthonormal list is linearly independent, and it follows from this, right? So suppose that like V is 0, right? Suppose that V is 0. If E1 and En, if E1 to En is linearly independent, then this must imply that Vk is 0 for all k. Can we show this? Well, we can, right? Because the norm of V, the square of the norm of V was this. And if V is 0, this must be 0, right? The norm of the 0 vector is just 0. But because these are all squared, absolute values squared, that means that they're all positive. And because they're all positive, if they add up to 0, they must all be 0. So v1 equals 0 all the way to vn equals 0. So that means that v is 0. No, sorry. That means that e1 to en are linearly independent. So then if you have enough of these vectors, we're going to have an orthonormal basis. So they're going to span the whole space. Okay. So on the topic of orthonormal bases, suppose we have one, right? So suppose we have some n-dimensional inner product space, and it has an orthonormal basis e1 to en. That means that every vector in V is equal to some linear combination of these vectors. Can we get the coordinates, right? And it turns out we can, right? So if you multiply V by EK, what is that going to be if you expand this out? How would I explain this? Yeah, if you expand this out, right, this is going to be equal to A1, E1, all the way to EN, EN of EK. By homogeneity and additivity, this whole thing is A1, E1, EK plus all the way to AK, EK, EK plus all the way to AN, EN, EK. Now notice, because these are all orthonormal, all of these terms are 0, except EK, EK. And as we said, because that's, remember, this is just the norm of EK squared, and that's 1. This whole thing is 1. So the inner product of V and EK ends up just being equal to AK, that is the kth coordinate of V with respect to the spaces. So that means that you can write any vector, if you have any vector in V, so any V in V, we can find its coordinates with respect to the spaces by this technique, right? So what's the coordinate with respect to the first basis vector? That's going to be V, E1, and where's E1? So that's the first coordinate. The second coordinate is V2, not V2, is V, E2, from Z2 all the way to V, En, En. Right, so any vector can be written in this way as a linear combination of the orthonormal bases. And as we said before, from the Pythagorean theorem, what we know is that the length of V, well, an arbitrary vector V, is going to be equal to all these coordinates squared. Their magnitude, we get the magnitude, then we square them. And this is getting a bit cluttered. Right? So we have that. So we have that the square of the normal V is equal to this. What if we cut it, right? What if we say we only go up to n? If we only go up to m and ignore everything after that, we're going to get something smaller on this side, which means this is bigger, so we have an inequality. And this is Bessel's inequality. What time is it? Jesus, 4:46. It's been an hour. Okay. What are the other stuff you have to prove? Oh yeah. Oh shit, Gram-Schmidt. Gram-Schmidt is. Oh man. Okay. That's important. Okay, so I'm gonna do something first, then I'm gonna do Gram-Schmidt. So when I said duals, this is where we're gonna get to duals. So just a quick refresher. If you have a vector space V, its dual basis is denoted by V prime, and that's equal to the list of linear maps from V to the field over which it is defined. And well, usually what we did is if you had a basis in V, right? And in this case, let's say we have an orthonormal basis in V, and V is an inner product space, right? So we have this orthonormal basis E1 to En. To each of these basis vectors, you could associate, what is it? A linear functional, right? A member of V prime, phi1 to phi n. That would be a basis of the dual space, and we would call this the dual basis. And each of these was defined in such a way that if you had, say, phi k of, you know, like a1, e1 to an, en, this would be equal to the kth coordinate of this vector, And the kth coordinate of this is just ak. This should remind you of something, right? This should remind you of taking the inner product with the kth orthonormal basis vector. So in this way, if you have, say, phi k of V, that's equal to the inner product of V with the kth basis vector. And since this is a basis of the dual space, any phi, any linear functional can be written as a linear combination of these vectors. So that would be, I use A there. Yeah, I use A, I'm going to use B here. So B1, phi 1 of V, all the way to Bn, phi n of V. But because we wrote phi, the index phi's, using the inner product, we can say that this is equal to B1, V, E1, all the way to Bn, Ven. And then using the properties of the inner product, you can simplify this to V. Okay, I'm gonna leave the algebra to you guys, because remember that has to be conjugated. And because E1 to En is a basis, that means that this is a unique vector, let's just say W in V. So that means that any linear combination, not a combination, any linear functional in the dual space can be written as the inner product of its input with some other vector W. And any linear functional can be uniquely identified with this vector. And this is the Riesz representation theorem. It's apparently important, but I don't know why. Okay, now Gram-Schmidt. Gram-Schmidt is actually, I actually know why it's important. Let's go on. Okay. Gram-Schmidt. Any comments, questions?
I do have a quick question.
All right, go ahead.
For orthonormal bases, are they unique for each vector space?
No.
No?
No, because I don't want to dirty up this one. So for example, if you have R2, well, you have I hat and J hat. Suppose you take like this vector, right? And it's going to be like root 2, root 2. It's going to lie on a circle. And then you take this vector, rotate it by 90 degrees.
Yeah.
And that's an orthonormal basis.
Okay. I see.
Yeah.
Thank you.
So it's not unique. Okay. Okay, nothing from Evan, so we're gonna move on. Okay, Gram-Schmidt. Okay, so this is important. I was gonna do an example for this, but I'm not going to anymore because I'm tired. Okay, Gram-Schmidt. I'm gonna leave the energy for something else. So the question is, if you have these vectors, the Gram-Schmidt algorithm, right? So I have two short ones. We have a vector space V, finite dimensional vector space V, and because it's finite dimensional, it obviously has a basis of length n. Now this basis isn't guaranteed to be orthonormal, or I should say orthogonal. The question is, we want to find an orthogonal, that's important, an orthogonal basis for this vector space. Because when we find the orthogonal basis, we can just divide each of them by their norm, and we get an orthonormal basis, right? So how do we do that? Okay, so the guide of our intuition is always R2. So suppose we have two, we have a basis in R2, right? So we have these two vectors. And we want to use them to find an orthogonal set of vectors that span the whole space. Well, one thing we can do is, and I'm going to call this V1 and V2. We can draw like a line perpendicular to V1. And the way you can find a vector on that line using only these two vectors is, notice we can add a scaled version of V1 to V2 such that it lies on that line. The sum of V2 and that scaled version, we're going to call it alpha V1, lies on that line, and it's perpendicular to V1. Formally, what does that say? We say that you want to find alpha such that V2 plus alpha V1 is orthogonal to V1. That is, this is 0. So once we do that, we can find an orthogonal basis for R2, or any two-dimensional space. And doing that is, it's pretty simple. You just expand, you get V2, V1 plus alpha V1, V1 equals 0. Solving the equation, we get alpha is equal to negative V2, V1 over, and you have to divide by this, right? And that's just the square root of the norm of V1. So what we found is we found this vector and we found this vector, and they are an orthogonal basis for this two-dimensional space. So in general, if you have an n-dimensional space, what we can do is we just keep applying this. So the first vector we're going to choose for our orthogonal basis is going to be V1. And then the second one, we just do that. And that's going to be V2 plus alpha V1, right? It's going to be V2 plus alpha V1. What is alpha? Alpha is V2 V1 over normal V1 squared times V1. I'm gonna replace, because we said E1 is equal to V1, I'm gonna replace all these V1s with E1. Okay, now we want to do this for more spaces, like so for three-dimensional space. What do we do? So we can sort of see a pattern here, is we have E1 is V1, E2 is V2 plus something, and we use the coefficient there. One thing we can do is we can say, let's say, E3 is equal to E3 plus alpha V2 plus beta V1. And I'm not, no, actually, no. That's E1, right? So I'm going to put E2 here and E1. Now we know E2 and E1, we can use this to find E3. So the question becomes finding values of alpha and beta such that E3 is orthogonal to E1 and E2. That's two sets of equations, right? So we have the equation E3, E1 equals 0, and we have the equation E3, E2 equals 0. And we have two unknowns. So we can solve that system. This one, E3 and E1, well, what does that become, right? So we have V3, E1 plus alpha, E2, E1. You should notice cancellations here. Plus beta, E1, E1. Well, E2 and E1 are orthogonal. That's 0. And this whole thing is supposed to be 0. So we get a linear equation in terms of B, which we can solve. Not B, beta. Which we can solve, and we get E3, E1 divided by, that's the norm of E1 squared. That's the first part. And notice, because we're not in an orthonormal basis, we're finding an orthogonal basis. That's not necessarily 1. You have a question? No? All right. And then the second equation would be E3. Okay, we're gonna, so E3 and E2, what would be the inner product? It's gonna be V3, E2 plus alpha E2 plus beta E2, E1. That's 0 because they're orthogonal. And the whole thing is going to be 0. Therefore, alpha is going to be negative V3, E2 divided by the norm of V2 squared. So now we can write E3 in this way. We can say that it's V3 plus alpha is, well, not plus, minus E3, E2 squared times E2 plus, I need more space, plus beta E1, which is minus V3 E1 divided by E1 squared E1. And you can sort of perhaps notice a pattern here, because well, we have E1 is equal to V1, E2 is V2 plus something, E3 is V3 plus something. So in general, we can say that AK is probably equal to VK plus something. Well, not, these should be minus something, but the index is the same as the one up here. So I'm going to say EK minus 1 squared times EK minus 1. And then we keep subtracting this by 1 until we get to 1. So we get and you can prove this by induction. I'm not going to. But yeah, this is how you go from a normal basis to an orthogonal basis. And then if you want an orthonormal basis, you just divide each of these by their respective norms. Okay, my battery is at 5%. Should probably do something. Okay, Evan left. Great. Okay.
Is that it for today's session?
No, there's more.
Okay.
Yeah. I mean, like, if you guys want to leave, like, I mean.
No, yeah, I'm gonna stay until the end.
You have a charger?
I think there's a,
Oh.
yeah, oh yeah.
I'm gonna keep streaming. Maybe someone will watch it. What is this? It's gonna fall. Okay. And okay, what is left? What is left? I'm gonna skip a bunch of stuff that I haven't even read before. Then the Rees representation. You don't care about these. Okay, orthogonal complements. Okay, I'm only gonna do the necessary stuff. I'm not gonna do any of the other stuff from now on. What time is it? It's 5. Yes, okay. Went a bit slow. When Robert's here, like Robert just like, you know, go faster, and then when he's not here, you know, go slow. Oh yeah. Okay. Orthogonal complement, right? So if you have a subset U of V, then its orthogonal complement, to be denoted by that, is the set of all vectors in V that are perpendicular to all vectors in U. Right? So if you want an example, right? So if you have 2D space and you have a line in it, what are all the vectors perpendicular to all the elements in this line? Well, this line, the perpendicular line to it. And certain properties. So as you know, 0 is perpendicular to everything, right? So its orthogonal complement is everything. And because it is the only thing orthogonal to everything, the orthogonal complement of the whole vector space is going to be the 0 set as well. And if you have U, its intersection with its orthogonal complement, it's going to be trivial. I mean, this is an example of that. Why is that so? Okay, so suppose like x is in this, right? Then x has to be perpendicular to itself. That means that this has to be 0. But the only thing perpendicular to itself is 0, right? So x has to be 0. So the only vector in this is also the 0 vector. And this is a suggested example because you see if this is U and if this is the complement of U, the orthogonal complement of U, these are direct sums, right? Right, so U and the orthogonal complement is a direct sum. Well, at least it's a sum, so it spans V, right? And then it's direct because we said that this is equal to 0. Am I gonna prove in detail? No, I'm not gonna prove in detail. Okay. So that's for orthogonal complements. Oh, and the dimension? Dimension, yeah. So because V is equal to the direct sum of these two, then the dimension of V is equal to the dimension of U plus the dimension of the So the dimension of the orthogonal complement is dim v minus dim v.
So by U, you mean all the, wait a second, actually, U represents many vectors, right? Not just one vector?
Yeah, U is a subset.
Yeah.
So, or a subspace. So in this case, U is a subspace.
Okay.
And then, oh, and because this orthogonality is it's a commutative relation, right? So if x is orthogonal to y, then y is orthogonal to x. So this means that, this implies that if you take the orthogonal complement of u and take the orthogonal complement of that, that's just going to be u. Right? Because everything orthogonal to this is in u, and everything orthogonal in this is in this. Yeah. Ran out of time. And then orthogonal projection. Okay, this is the interesting thing. Okay, so if you have a subspace U of V, we can define a linear map, PU, based on that. It's going to be linear. What does this do? So if you have, we said that V is a direct sum of U and its orthogonal complement. So we can define this projection map. It takes V. Let me put it like this, right? So any V in the vector space V can be written as the sum of a vector from U and a vector W from the orthogonal complement of U in one and only one way.
Yes. What does P of U stand for? Could you please explain?
We're gonna get to it.
Okay, and then could you also explain the subspace notation? I guess it was just never covered for me. What does
This?
no, just the sideways U with a bar or without?
So
what's the difference?
Was this in A67? No, I don't think it was. So if you have a set U, and if you have a set W, and when you say that U is a subset of W, that means that everything that's in U is also in W. So in pictures.
Okay.
Yeah, and then, but in this case, I was using it as a subspace. So that means that both of them are spaces, vector spaces, and then they're subsets.
Okay.
Right? Yeah.
And if we do it without the bar underneath, I guess just the
So this it's sort of like this, where it could potentially be the same set. They could potentially be the same set, but if you ignore that, if you don't have that, then that means that they're necessarily distinct.
Okay. Thank you.
And so because they can be written in one and only one way, we can define this linear map, and this is the set U, that PU takes V to U, right? Right? So geometrically, what does this mean, right? So if you have a line U, this is an R2. If you have a line U, and you have its orthogonal complement, then you have some vector V, right? So this vector V can be written in one and only one way, as a sum of vectors in U and the orthogonal complement of U. So you have that thing, right? And that's in U, that vector's in U. And then you have this thing, that vector's in the orthogonal complement of U, and their sum is V. What is PUV? It's called the projection map for this reason. It gives you this vector. Whenever you give it a V, it gives you that vector. So you can think of it as like dropping a perpendicular from V onto this line and finding that point. Then the arrow from the origin to this point is the vector that it gives you.
Okay, but why not U? That's the perpendicular symbol. I forgot.
Well, that would be this map.
Oh, okay. Then yeah.
Yeah. Okay. Why is this important? This is the only cool part of this chapter. Why is this important? We can do cool things with this. So, wait, do I need to do anything before that? Oh man, I need to prove shit. Okay, I should not have erased the picture. Some background before we can do the cool things. So you have PU. What if you put in a vector that's part of U? What do you think that would be equal to?
I don't know.
So what is a vector? So if U is in U, the big U,
Yeah.
it'll be something like this, right? Like you see.
But then don't we need the perpendicular vector?
Yeah, right, so because it's a direct sum, U is equal to like some x plus w, x plus y, where x is in U and y is in orthogonal complement. But the thing is, we already said that U is in U.
Yes.
That means that y has to be 0. Y is the 0.
Oh, okay. And
Right.
then
So this would be what?
that's just U.
Yep, that's U.
Okay.
And you can think of it this way, right? So projecting U onto itself just gives itself. And so what about PU squared, right? If you square that and you give it any vector x, so this is equal to what? This is equal to doing PU of x. So once you project it onto U once, the second time, it's going to be already on U. So this thing, it's in U. Because it's in U, this whole thing is also in U. Right, so
it equals or it's also
No.
in U?
it is equal, it is equal.
Okay.
Yeah. And then for the same reasons, right? So if you have W in the orthogonal complement, then projecting it onto U, because notice if you have a vector W here, and you project it onto U, you bring it down, it's just gonna be the 0 vector.
Okay.
Yeah, so PU of W is 0, if W is in the orthogonal complement.
For that specific example?
No, in general.
In general.
Yeah, so because it's just you drop a perpendicular from V, the projection map is like this. You drop a perpendicular from this point onto the line U, and you find the intersection, and you draw an arrow from the origin to the intersection. That's the result of the projection. It's like, you can think of like a light source really far away. What would the shadow of this vector be on the line U? The shadow, right? So, like in this case, I have this. The shadow looks like a line, right? Same idea there. Lastly, okay, so if you recall, if you said we have an orthonormal list, and this orthonormal list spans U, this U, then all the vectors in U, right? So any vector U in U can be represented in this way. So U is equal to U E1 plus all the way to U En. And then if you have any vector, not even in U, so just generally in V, its coefficients on E1 to En will be given in this way, right? So you can write V is equal to VE1 E1, En, En plus some other stuff W, right? And then this, because E1 to En is the basis of U, this is the part of V that lies on U. So that's the projection. So this thing is equal to the projection of U onto V. Does that make sense? That's the only important part of this.
No.
No? Okay.
Maybe would you mind restating it again?
Restating it.
Yes. Just
Okay.
explain it.
So U has a basis,
Yes.
E1 to En, and it's orthonormal. So do you understand that if you have a vector V in V, and you write it as a linear combination of this, right? So you can say V is equal to A1, E1, AN, En. Then the inner product of V with EK is equal to AK. You understand this part?
First question, how can we write it as some vectors from U if it's in another vector space?
Well, we said that U is a subspace of V, right?
Okay, that, yeah.
Right.
Then the second part, I don't really understand. I think you explained it earlier, but then...
I did, but now we go quickly, right? So, okay. So if you have a vector in V, right?
Okay.
In V, and as we said, V is equal to U, and it's direct sum with the orthogonal complement of U. That means that so V, any V in V is equal to some U plus some W, and this U is in the subspace U, and W is in the orthogonal complement. So this is a basis of U, right? Which means that it can be written as a linear combination of these vectors, right? So it can be written as A1, E1, all the way to AN, En. And then W, we leave it there. What if we take the inner product of V with EK? So by homogeneity and additivity, we can expand this, right? So we get A1, E1, EK, all the way to AN, EN, EK, plus what? Oh, plus W, K. So, what is this?
A times E1 EK. Wasn't E1 EK 0?
Yeah, because they're orthogonal.
Yeah.
Yeah, so it's 0. We can cancel out all of these except one, and that's the kth one, because the inner product of EK and EK is 1. So this whole thing is equal to AK and the inner product of EK and EK, which is just 1, right? And this last one, but notice W is in the orthogonal complement, and EK is in U. It's a basis of U. And anything in the orthogonal complement is orthogonal to anything in U.
So
That means these two are orthogonal.
0?
Yes, 0.
Okay.
So you see that?
Yes.
Okay, so that means that once you have any vector, the part of it that is PUV is just this, right? So what we can say is, we can say that PU applied to V is equal to V E1, E1 all the way to V En, En. Okay, now onto the cool thing. Reeves wrote, nobody cares about that. Okay, so, okay, minimizing distances. Like I said, right? So if you have a point and you have a line in Euclidean space, the shortest path between that point and the line is the line that's perpendicular, right? So we can use our intuition for this to come up with something more general, right? So you have this 2D space, you have this point, V, and you have a subspace. And the subspace is a line, in this case, U. And suppose you have some point in the subspace, it's big U, we're going to call this U, small u. And we draw this arrow here, that vector. You can move u along this line. Where could we put it to minimize the distance? You can sort of imagine moving this along. Some points, like around here, it's got to be minimized. Does that make sense?
Yeah.
And where is that? Do you remember what this vector was? When we draw up a perpendicular,
Yeah.
it intersects the subspace, and we draw an arrow from the intersection to the origin. What was it?
It's just it's kind of like.
Yeah, it's very fast, I know, but
Yes.
I mean, the diagram kind of looks similar, no? You see that? And then this.
It kind of does, yes. So that would be P U of V.
Exactly.
Okay.
So this vector here is the projection of V onto U. So what, and we're going to show that the length of this vector, that is the length of V minus projection of U1 to V, is smaller or equal to the distance of V from any other vector on the subspace.
So you say we have to show that it's not.
Yeah, because in Euclidean space, we just know that from geometry, right?
Yes.
But we're working in an abstract space, so we use the diagram to just sort of develop our intuition.
Mhm.
And in this case, it works out pretty well, right? Because you know that this is perpendicular.
Yes.
And so if this were Euclidean geometry, what you would do is you would say, okay, this length is A, this length is B, this length is C. Because it's perpendicular, A squared plus B squared is equal to C squared. And that means that A squared is equal to C squared minus B squared. So if you ignore this B, right, that means that this part becomes bigger, this stays the same, so this becomes an inequality. That looks similar, right? You went to this, this, right? So now, and we use the Pythagorean theorem, right? The proof in an arbitrary vector space is the exact same thing. We just have to use different notation, right? So this vector is u minus PUV, and this vector is v minus PUV, and this vector is, what is it? It's v minus u. So from the Pythagorean theorem, we know that v minus u squared is equal to this squared plus this squared, the length of them. That's u minus PUV squared plus v minus PUV squared. And what we did by this point is we moved, if you remember the previous one, we moved this one to the other side. So we said that v minus PUV squared is equal to v minus u squared minus u minus PUV squared. And then if you ignore this, this becomes an inequality. You have this.
Quick question. So I think you lost me there a bit. Why is the projection of V onto U equal to V minus PUV? Well, that's vertical
Wait.
perpendicular line to U.
What is equal to what?
The perpendicular line to U, you said it's equal to V minus PUV.
the perpendicular line to you? To you?
To
Oh, the line u.
Yeah,
oh,
this
so
line.
so this vector is the projection,
That one, yeah.
and then you remember from high school, the difference of two vectors is the arrow connecting them.
Yes.
Right, so you have v, we have pu of v,
Okay.
and then the arrow connecting them is that.
I see.
Oh, yeah.
So, yeah, okay, go ahead.
Yeah, so we've shown that this distance is shorter than that distance for any choice of u. Shorter or equal to.
And why are we allowed to use the preceding figure? Is it because it's
Yeah, perpendicular.
Okay, but then in abstract spaces, how can, for instance,
But we showed that because that's how we define PUV. We define it in terms of u, and it's orthogonal. The orthogonal complement of u.
Okay.
So v minus PUV is always, I should mention that, right? So if you have, that's v, right? That's PUV, and v minus PUV is this vector. What about P of, wait, let me find out how I explain this. It's a direct sum, right?
Yes.
So when you write v as u plus w, u is in u and w is in the orthogonal complement of u. That means that w is in the orthogonal complement of u. And because it's in the orthogonal complement of u, it has to be perpendicular to any vector in v. Right? And if you look at this, these are all vectors in v, in u. Yeah.
Okay.
I mean geometrically, right? So if you, just with the intuition, right? That's not a rigorous proof. But that's u and this is the orthogonal complement of u. You can see that this is parallel to this.
Yes.
That means that it's in.
Okay.
Yeah. Okay, do you want an application of this?
Up to you, really.
Yeah, I mean, if you got time, you can do linear regression, an actual real-world application.
It's just, I don't know, what confuses me is the notion of two vectors being perpendicular. Because I thought when vectors are perpendicular, that applies only in Euclidean geometry. For instance, how can functions...
So we defined perpendicularity. We chose a new name. We called it orthogonality. And
oh, yes. Okay, then, yes.
yeah, and then
itself really
it's the analog. It's the generalization, right? If you have two vectors whose inner product is 0, we say that they're orthogonal. And this was an arbitrary definition. We chose it because it was convenient. Okay, now. Okay. Linear regression, an actual honest-to-God application in this for a second book. Okay. Okay, so you remember line of best fit in like science? High school science?
maybe.
So, I mean, you would do like an experiment, and then you would get a bunch of these data points. So this would be x-axis, y-axis, and like,
Oh,
I don't know.
I do.
Yeah, and then this could be anything. Like, it could be like, I don't know, temperature of water, and then y could be like, I don't know, amount of substance produced in the reaction, in like chemistry, right? And you would do an experiment, and you would get a bunch of data points, something like that, spread around, and you were then asked to sort of find a line of best fit, and then maybe extrapolate, right? See if you had, okay, some x value that you didn't do an experiment for. What would be a good guess for the y value associated with that? And what you would do is you would kind of sort of draw a line visually, and so okay, for this x value, right, we just, that would be the proper y value, right? That would be a guess.
Okay, so now I'm guessing that with linear algebra we don't have to do it visually. We can calculate.
Yeah, we can calculate the best line.
Okay.
Exactly, and okay, so suppose the data points we have, so all these points, they have coordinates, right? We say those coordinates are x1, y1, x2, y2, and onwards until xn, yn. So we've done n experiments, or n trials. We can write these as vectors, right? So our inputs will be, say, x1 all the way to xn, and our outputs are going to be y1 all the way to yn. And we want to find the linear function, right? And to simplify our case, I'm going to say it passes through the origin. If you don't want it to pass through the origin, you have to do calculus. I don't want to do calculus. So let's say the equation of this graph is something like fx is equal to ax. It's a line, it passes through the origin, that's the equation. The question is, you have a question?
No.
Okay, so the question is, what is the best choice for A to get it to be, perfectly around these things? So what we have to do is suppose we use this to approximate what y's would be, right? We've done some experiments, we know the actual y's, but given these inputs, we want to sort of compare them. This is training, right? So if you have like machine learning, you train it on previous data. This is our previous data, and we're going to train our model based on the data that we have. But first, we see how our model acts on the current data, right? In this case, we can have like a linear map, Tx is equal to Ax. Ax, which in this case would be Ax1 all the way, Ax2 all the way to Axn. And this is going to be our estimate, right? We're going to call this an estimate. I'm going to use y hat to denote it. What we want to find, what was it supposed to do now? Okay, so we have these are vectors in n-dimensional space, right? Let U be the span of X. So it's a line in n-dimensional space. For intuition, I'm going to use two-dimensional space. But yeah, let's say that's U, right? And then we have this Y thing, right? So that the results of our experiments, Y. And notice that our estimate is a scalar multiple of X. So it lies somewhere on this line U, right?
Yeah.
And the question is, what choice of U would be best? Well, what choice of A? So if you have this, we're going to call it y hat. In statistics, they use y hat to denote an estimate. We can sort of move this along based on the value of A, and we want it to be where it's orthogonal to, that is, we want the line y minus y hat to be orthogonal to y hat.
Okay.
Right? And, well, based on the result that we just proved, we said that it was y minus projection of u at y is the best choice. Right? It's less than y minus y hat for any estimate. So this is basically where we want it to be. So what is PUA? PUY. PUY, if you remember, is it still written here somewhere? It is not written here somewhere, but if you remember, we could write PUY using the inner product, where, okay, first we have to find an orthonormal basis for U. So U is one-dimensional, so that's already orthogonal. We need it to be orthonormal, so we just divide it by its norm. So that's the orthonormal basis for U. Then PUY is, if you remember, the coordinate would be y multiplied by E1, right? In this case, E1 is just x over the norm of x multiplied by x over the norm of x. That is E1. And remember, right? So we said that A, that is the best estimate, and the best estimate they write like this, right? In statistics. The best estimate was supposed to be AX, right? And we know that it's this, right? So we know that AX, the best estimate we wanted to find, is equal to the inner product of y with x over the norm of x times x over the norm of x. So what is that? How do you compute that? I'm tripping. Oh yeah, okay, so we have these, right? So we have y is this vector, and we can simplify this, right? Because this is the real inner product, and 1 over the norm of x is a real number. We don't need to conjugate it. We just take it outside, and we have another one here. So the norm is squared, and then we have the inner product of y with x times x, right? I'll put x here, times, what is the inner product of y with x? That's just the dot product. What is the dot product? It's the sum of the pairwise products, right? So xk, yk. So now we know that ax is equal to x over, or another way. It's this is just the square root of the norm from the inner product times x. Therefore, this thing is A. So we found the slope of the line of best fit. And that's using linear algebra. And that's linear regression. And you can do this for n dimensions as well, but that would have taken too long, so you only have the 2-dimensional version. And if you want an example with distances for functions, is in the problem set. The idea is, here we use a line to approximate a data set. There we use a function, a sum of trigonometric functions, to approximate an arbitrary continuous function. Right? It's like approximations. Yeah, and we find the best approximation. Yeah, that's it.
I see.
There's some other stuff, but we skip those. I don't care. This was the only interesting thing. I just wanted to do this and then ditch. Okay. Yeah, now I gotta erase these. Oh yeah. I should end the stream.
Whoa, so